Welcome back from the coffee break. Now we have a talk by Hugo Mosquera on de Sitter, anti-de Sitter, and all that.
Okay. So I thank Mario for organizing the school one more time. And before starting, let me tell you that this is supposed to be the first of two advanced seminars. But I will maintain the promise, and I will tell you about some recent results which are even not yet published. But I will do this in the last 5 minutes of my talk of tomorrow to entertain the suspense, let's say. So what I will do is today I will make a general presentation about the sitter, little of anti-de Sitter also. I will talk about very basic things which, in the way I will tell you, are not known, even I think it should be the opposite way, even to experts working in the subject. So if you, for instance, open the Birrell and Davis book or similar books about quantum field theory and curved space-time, we won't find the information I will give you, even though are very basic information. And then, starting on what I will tell you today, tomorrow I will present some recent results, which I find very interesting. At least they interest me. So let me start. Doesn't work. Ah, yes, it works. So we saw this equation many times. You all love it. This is the Einstein's equation. These are the Einstein's equation with the cosmological term, which was introduced a little more than 100 years ago. It is the first modification of general relativity, since we are looking for modified gravity theories. This is the first modification of gravity theory made by Einstein himself. And you know maybe how he came. And this is a statement that you can find in the book. The title is Albert Einstein, Philosopher Scientist, which was offered to Einstein as a gift for his birthday. Contains contribution of many people, and in particular, there is a contribution by this priest, this Belgian priest, which is Georges Lemaitre. At that time, he was the only one to still believe in the cosmological constant. If you look in his contribution, there is this statement in which he says that in the history of science, many discoveries have been done for reasons which are no more satisfactory, and it could be that the cosmological constant is such a case. This is a statement of 1949 by Lemaitre, and in answering to this statement, Einstein in the same book says that he could not believe that nature could create such an ugly thing. Einstein never said that it was the cosmological constant was his bigger mistake. This is something that you heard about, but he never said this, but he wrote that the cosmological constant is an ugly thing. So, I don't know how to use this thing, by the way. Ah, okay. So, if you solve this equation, and I will do it with the zero matter, just the cosmological constant, a positive cosmological constant, the nice fact is that you can visualize the solution by using an embedding in a Minkowski space which has one dimension more. So you take this manifold in a Minkowski space with one dimension more. So you see, this is the d-dimensional de Sitter manifold. This is a d plus 1 dimensional Minkowski space-time. This is the Lorentz group of the ambient space-time, which is going to be the relativity group of this manifold, which is invariant, of course, under the Lorentz group, not the Poincaré group, but the Lorentz group of the ambient space. And this is the de Sitter universe. If you allow a negative cosmological constant, you can also visualize a corresponding solution. For a negative cosmological constant, you take an ambient space which has 2 time-like direction and d minus 1 space-like direction. In this case, the Lorentz group, let's say, would be Lorentz group of the ambient space as 2 time-like direction. And this is going to be the relativity group of this manifold, which, even if it is not obvious looking at this figure, is a Lorentzian manifold. So it is a space-time, 1 time-like direction. So I will make a few comments about the anti-de Sitter later, but I will focus on the de Sitter case. So how it came that I add this historical part because to make contact with what Mario Novello was saying yesterday, the cosmological paper by Einstein arose in a discussion between first Einstein and de Sitter, and then with other people at that time in a famous debate concerning the so-called relativity of inertia problem. So it was to test the Machian ideas that Einstein introduced his cosmological model, which is the first cosmological model in modern, say, cosmology, is the birth of cosmology. And these are the requirements that Einstein made. He wanted the universe to be static. Now you can blame it for this assumption, but at that time the fixed stars were fixed. Everyone believed that the universe was static. And this was the major, let's say, the major epistemological assumption is that in a consistent theory of relativity, there should be no inertia relativity to space, but only inertia of masses relative to one another. So there is no, so if you want to solve the Einstein's equation, as you know, since they are they set a Cauchy problem, even though a complicated one because of the presence of constraints, you have to impose boundary conditions. And boundary conditions are a remnant of absolute space. If you have not, so this would mean that the metric should depend not only on the position of the masses, but also of the boundary conditions. So what to do to solve this problem? And you know what Einstein did. The crazy idea was to get rid of the boundary. So he's assumed that the universe was spherical. Spherical means a 3-sphere embedded in a 4-dimensional Euclidean space. So a curved sphere, not a ball, but a curved sphere in 3 dimensions. So this assumption was made by Einstein to get rid of the boundaries. So once you do this assumption, you cannot solve the Einstein equation to get a static solution. And that's why he had to introduce the cosmological term. And this is the first cosmological model, is the Einstein cylindrical model of the universe. And you see that indeed, as the idea that Mario was pursuing yesterday, the mass, the total mass of the universe, which is proportional to its radius, is also proportional to the cosmological constant. No mass, no radius. No mass, no universe. That is the virtue of the Einstein cosmological model. So once more, the point was that to to have a closed static universe, you need to introduce the cosmological constant. While, if you read the paper by Einstein, the cosmological paper, you will see that he was perfectly aware of the fact that if you don't impose the staticity condition, there were expanding solution of the universe. This is written in the first paper by Einstein. He says if you renounce the staticity hypothesis, you don't need to add the cosmological constant. There is a mistake in that paper, but it's not at this point. Okay, so the discussion was with De Sitter, and De Sitter immediately realized that the new equation by Einstein had an alternative solution. And you will be, I don't know if you had the opportunity to read the 3 papers by De Sitter where the De Sitter space-time is introduced. And in the first paper, you will be surprised to understand, to see that he introduced the paper by a Euclidean rotation, a big rotation, before quantum mechanics existed. So he took the imaginary time. So because he was commenting the solution by Einstein concerning the problem of the boundary, of the solution of the boundary condition by Einstein, and that solution was not covariant. So he proposed a covariant solution. How to do this covariant solution? By considering a sphere in 5 dimensions, in which the first dimension is complex. So the first appearance of the De Sitter universe in the first paper by De Sitter is true, is Euclidean section. So this, as you know for sure, this solution Einstein did not like at all this solution, and tried to kill it in several ways, because this solution is anti-Machian. It's completely anti-Machian, so there is a universe with no matter at all. While the idea of Einstein is that the universe could exist only if matter exists. So Einstein tried to kill this solution, and in particular, he made several comments which were not correct, and in particular, one criticism was about the fact that this solution is not static. So these are words by the correspondence between Einstein and De Sitter, because maybe you know that at the time people wrote letters to each other, like we do with emails, and you may be surprised that they wrote 2 letters in a day and get the answer the day after, you see. So the discussion was really tight without internet. And the advantage is that now we can read those letters, while our emails will be forgotten forever, apart from people looking at us from the United States. But we will forget. They won't. Okay. So in the second paper by De Sitter, indeed, he found the static presentation of the De Sitter metric. See, this is a particular coordinate system of the De Sitter manifold, which covers only this region, and you see it is generated by one subgroup of the Lorentz group of the ambient space. The blue line is the only geodesic here, and this region is like a black hole. And you see, if you take the ambient space metric and you use this coordinate system and you write the De Sitter metric in these coordinates, it looks like the Schwarzschild solution, more or less. Of course, it's not the Schwarzschild solution, but it has similar shape. This metric appears in the second paper by De Sitter, answering to the problem of the staticity of this, the non-staticity of this new solution. And you see that here the coefficient of the metric do not depend on time. So there is a portion of the De Sitter manifold which is static in this coordinate system. But you see, the red lines here set another issue. So the whole discussion was, these are the horizons, of course, and I will tell you something about this fact in my advanced seminar of tomorrow, some new results that I have on this point. These red lines, so there was the discussion if there was a singularity here. So Einstein said, you see, there is a singularity. This is not a vacuum solution, because at that time, general relativity was just born, and people were not used to diffeomorphism invariance. So what was physical and was just artifact of the coordinate system you choose was not obvious. So in the end, Weil also entered in the discussion, but the controversy was solved by Klein, and showing that it was completely regular, a solution of the Einstein's modified equation. So there was this anti-Machian solution, but in the end, Einstein still dismissed the solution because it was not globally static. So it is really interesting to read this correspondence and to read also the effect that prejudge, the epistemological prejudge by Einstein, as they played a double role for him. They play a major role in the discovery of general relativity, but also set some difficulties from to him to move out of his previous convictions. Okay. So now we are after this year. In this year, the cosmological constant bounced back in the physics literature, at least, if not in physics. Maybe Robert said that he does not believe in the cosmological constant, but if you look at the literature in theoretical physics, you see that I would say that 50% of the papers are concerned with this problem from one side or the other, because in the same year there was this paper appears in 1998, so exactly 20 years ago, but the preprints are of 1997, so exactly 70 years after, 70 years? No, 80 years after the paper by Einstein. So in these two papers, this is a positive cosmological constant that comes again in the play in physics and in theoretical physics, and in this paper is the negative constant, which in the same year comes back into the play. So now we are after this year, and we are used to think. Of course, there is Roland Trier who wrote papers on the cosmological constant. Who? Before. Okay, but so it's because I see him here. He was believing in the cosmological constant before this time, but all the astrophysics community shift from one day to the other, from 0 value of the cosmological constant to 0.7 in one night, overnight. I mean, more or less. I don't know if this reconstruction is completely correct, but more or less. No? They changed. In 95, the cosmological constant was 0. There was spatial curvature, maybe, but not cosmological constant. So let's now look a little bit closer so the Friedmann's equation were not available in the discussion between Einstein and de Sitter. They came after. Once you have the Friedmann's equation at your disposal, it is extremely easy to solve both for the Einstein cosmological cylindrical model and for the de Sitter universe. But if you don't have to devise some clever way to find these solutions. before the Friedman's equation were there, it was not so easy to find those solutions. But now we do have the Friedman's equation, so here there is a spatial curvature in this term. So there are three possible geometries coping with homogeneity of the space. The spherical one, which was indeed part of the game in the very first paper of Einstein, the flat curvature, and the hyperbolic negative curvature. You see, this is a space manifold because if you draw, everyone knows, but let me remind you that if you draw this light cone, the surface is completely outside the light cone. It's a space manifold. So if you solve the Einstein's equation, so today this is the standard picture everyone know, but let me just show that in future, if this picture of the lambda CDM model is correct, indeed the cosmological constant is the only term which is going to survive. If this picture is exactly correct, all this part of the population of the universe will disappear, and this will take all the place. So we can solve the Friedman's equation using just cosmological terms, and there are three possible solutions. So if you assume that the universe is spheric, you simply solve this trivial differential equation, and you get the solution is hyperbolic cosine. If you solve with k equals 0, the solution is exponential. And if you solve with negative spatial curvature, the solution is hyperbolic sine. So three possible solutions. Yes?
I did not understand the previous slide.
Previous?
Yes.
This one? If the universe is expanding, these three terms are going, the denominator is going to increase, while these are numbers. So the denominator increases, so this term is going to go away, and the other is going to go away also. But the cosmological constant is constant, so it stays. If this model is correct, which is probably not correct, but if it is, the cosmological constant is the only thing which will survive in the universe. If we believe in this, of course. It's a crude, of course, approximation, but this is the standard model of cosmology as of today, which produces all these curves which we have discussed. So I said there are three possible solutions with these three different choices of spatial sections: a sphere, three-plane, and hyperbolic Lobachevsky space. But the interesting fact is that they all three are de Sitter. So if you choose this coordinate system, which is global on the de Sitter manifold, indeed this is the last coordinate system that was introduced in the game of de Sitter. Indeed. You see, you get this hyperbolic cosine and the spherical. If you make just the exercise on computing the derivatives here, you get this metric out of the ambient Minkowski space metric. So you get this hyperbolic cosine and the spherical section, as we show in the previous slide here. Hyperbolic cosine and the spherical section. This corresponds to this particular coordinate choice on the de Sitter manifold. So this is the case. Now you can choose the system of coordinates in which you make flat section. Parabola are flat manifolds. So these are the same as planes. So now our choice of time is this one. You see, x0 plus x4, this is the x0 axis, this is the x4 axis. Take this one proportional to your choice of time through an exponential. So you get this coordinate system. This are easy exercises you can do in your geometry first year course. And then you get that metric is the one you normally use in inflationary flat context. You see, you would say that this model, looking at this, you would say that this model has a bounce. Now looking at this, you won't say that this model has a bounce, but it's the same manifold. It's a piece of the same manifold, of course. But it's a piece of the same manifold. This remark is correct. But if you take not real, but complex coordinates, you cover the whole manifold. And finally, I'm sorry, I delete some. There is also the possibility of solving with the third case. You make another choice of time, and I don't know why there is no more the picture there. And you get also a portion of the de Sitter manifold as a Friedman universe with the Lobachevsky sections. Notice that in flat space you don't have these three choices. In flat space you can foliate Minkowski space by plane. So in this case, the exponential, the scale factor of the Minkowski universe is just constant. Or you can foliate with the Lobachevsky hyperbole the future cone of a point, and this is known as the Milne universe, and you get that the scale of the universe is just t. So for Minkowski, you have two possible choices. A portion of Minkowski, which is known as the Milne universe, is an open Friedman universe, and the whole Minkowski space is a flat Friedman universe. While in the de Sitter case, you have the three possibilities. So in this sense, it's more flexible. And in the anti-de Sitter case, you just have one possibility. So the anti-de Sitter case is also a Friedman universe with this scale factor, which has, of course, goes from 0 to 0. And it has just the possibility of it being described as a Friedman universe with open sections, so with the Lobachevsky spaces. There are many other possible coordinates. These are the usual ones you can find in textbooks. But there are other very interesting coordinate systems. This one I will come back to this particular one tomorrow when I will describe one recent result of mine on certain topological effects. So this comes out from the so-called Iwasawa decomposition of the Lorentz group, which acts as the relativity group on the de Sitter universe. And you see, this is not an orthogonal coordinate system, so you're foliating your system by spheres and by light rays. It's extremely useful, this particular coordinate system. So you can compare with this one. This is also global, but not orthogonal. And so it comes out, I will tell you about this tomorrow. And what is interesting to me, and I will describe a result about this, is that in two dimension, I will tell something about the anti-de Sitter just in a few minutes. But in 2 dimensions, there is a possible source of topological effects on the de Sitter manifold, because in 2 dimensions, the homotopy group of the space is non-trivial. So you can cover the de Sitter manifold in the space-like direction. So the covering group of the de Sitter group in 2 dimensions is SL2R. SL2R is the most studied group of the mathematical literature, I would say, and the quotient space of the SL2R with respect to this SO11 Lorentz subgroup is the double covering of the de Sitter manifold. This fact is at the moment okay. The most famous coset space of SL2R is the complex upper plane, which is the most studied in the mathematical literature. It makes gives rise to the Langlands problem, or so to say, to make an example, to the Langlands program. Here, if you make another quotient of the same manifold, you get this double covering of the de Sitter, of the 2-dimensional de Sitter universe, and this is very important to solve, to study solvable model of quantum field theory on the 2-dimensional de Sitter manifold. I will tell you something about this tomorrow. Other coordinate system comes if you try to solve, for instance, the equation of a string on the 2-dimensional de Sitter manifold, but then you can extend to higher dimensional. Okay, so I show you here other coordinate system which can be interesting. This coordinate system have the advantage of to give you already the let's say the worldsheet of the string. Indeed, here the worldsheet is the manifold itself, and you see it is expressed in terms of elliptic functions. These coordinate systems are not so trivial in the sense that they solve at the same time the equation of the string and the constraints. Here is for the closed string, but we can solve also for the open string, and we get things like this. So you don't have to think that those three, and even those two, probably you are all used to the spherical and to the flat coordinate system, are the only possible coordinate system. Here there are lots of coordinate systems, and all of them have virtues. So now we get rid of the coordinate system, and I'm going to describe some geometrical property of the de Sitter manifold just using the geometry of the embedding space, and a very important locus is the asymptotic cone in the ambient space, which is has the same equation of the de Sitter manifold, except that you put a 0 here. So the vectors lying on this cone are light-like in the ambient space-time sense. So if you so first property is that of course the light cone in the ambient space time provides the light cone ordering. So you fix a point here on your manifold and you draw the light cone of the ambient space-time. You know that this is the future, this is the past, and this is the space-like region with respect to this point. It's interesting. So this is one first observation. The second observation that you want to describe, for instance, the geodesics on the de Sitter manifold. So you can try to solve the equation. Of course, they are not impossible to be solved, but they are not so trivial. If you write this equation in one of those coordinate systems, solving them, it takes a little time. But you can just use geometry, and since the de Sitter manifold is a complex sphere, you know that the geodesics on a sphere can be obtained by intersecting your manifold with planes which intersect the origin of the ambient space. So these are the geodesics, but of course this is just a picture, but you can even be more precise. You see that for a time like geodesics, the plane intersects the light cone along two vectors which are light-like. So you can use these two vectors to parameterize your geodesics in this way, and tau is the proper time. So you pick these two vectors, and this is this geodesics and the other one. So why I'm telling you this, so you can elaborate a little bit. You can also write the geodesics in terms of one point here and one of those two vectors. So the number of degrees of freedom is, of course, the same. And this is to compare with the usual form of geodesic in flat space. So I'm telling this because I want to suggest that this light cone, these light-like vectors are going to play the role of momentum directions. Okay, so this is the natural momentum space for the de Sitter manifold. So that you can also describe light-like geodesics, of course. As I told you, so because since we have spoken about geodesics, we want to know how to compute the conserved quantities related to those geodesics, and all of them can be expressible in terms of these two vectors, two light-like vectors, describing the geodesical motion. So you can, for instance, pose problems of classical dynamics on the de Sitter manifold. You can solve a classical scattering problem in terms of these variables. I don't want to bother you with the details of how you do it. You simply impose conservation of this quantity at the scattering place, and then you get, for instance, if you study the decay of one particle into two particles on the let's say two-dimensional de Sitter manifold, you can completely determine these vectors. So here the particle decays into two. So this is the mass of the entering particle. These are the masses of the outgoing particles. These are the light-like vectors that you can construct in terms of these vectors. And you see that the process can happen if the mass subadditivity, the standard mass subadditivity condition is realized. So, I mean, the process cannot take place if the mass of the entering particle is less than the sum of the two outgoing particles. I'm, let's say, telling this because this property is no more true at the quantum level. At the quantum level, one particle can decay into two other particles irrespectively of their masses. I will tell you something maybe about this quantum process tomorrow. So, few words about the anti-de Sitter, since it was in my title. You can deal with the anti-de Sitter manifold essentially in the same way, even though the quantum field theories are completely different. They are nothing to do one with the other. But you can introduce the same thing. The light cone in the ambient space also plays an important role. Here, the difference is that this is not different in the sense that the light cone in the ambient space provides, again, the causal structure, which is now only local, in the sense that this region is a space-like separated region with respect to this point, and this is, in a sense, the future, but is, of course, also the past. So the light cone ordering on the anti-de Sitter manifold is only local. It's not global. You can understand better this. So it's causal, but not strongly causal. There are closed light-like curves, time-like curves, in particular closed time-like geodesics that you can visualize in this way, always in the same way you build the geodesics by intersecting the manifold with planes going here, with planes passing through the origin of the ambient space, and you see that this geodesic closes onto itself, And if you draw another geodesic like this, you can see that the geodesics exiting from one point all convene on the antipodal point. Okay? And yes? This is the time-like. Light-like goes towards the infinity. It goes toward the infinity. Touches the infinity. Of course, there is a space like infinity. Let me just go 2 slides forward. So here you see the two geodesics that reconvene at the opposite point. And all the geodesics exiting from a point go together at the antipodal point. So now, since my aim is quantum field theory on these two manifolds, they are really different, these two theories. In the de Sitter case, there is the fact that there is no lower bound on the energy on the de Sitter manifold, but this is not true on the anti-de Sitter manifold. So because there is no lower bound on the mean values of the energy, of whatever energy you define, let me say, because there is no canonically defined energy operator. But if, for instance, if you even choose the energy operator associated with this time translation here, even this operator is not bounded from below. So the absence of bound in the negative energies makes open possibilities which are not there at all in flat space. So thinking that the de Sitter quantum field theory has a little modification of Minkowski space quantum field theory is completely wrong. On the other hand, this is not true in the anti-de Sitter manifold, because in the anti-de Sitter manifold, the energy operator is bounded from below. And this is known to be the Friedmann-Breiten-Lohner bound. So they are totally different from this point of view. On the other hand, the difficulty of the anti-de Sitter manifold is that it is not globally hyperbolic. It is not globally hyperbolic in two senses. One, if there are closed time-like curves. Two, there is a boundary at space like infinity, which we can see using Perot's diagrams. So one way to curve this problem is that you say, okay, Einstein's equation only tells us about the local property of the geometry, but they say nothing globally. So you can, let's say, unwrap the time variable and pass to the infinite covering of this manifold. So this is the anti-de Sitter manifold, where you identify this point with this one. And this is the covered manifold in which you remove this identification. So the time is no more periodic. But of course, the geodesic still focus every pi, you see? So you don't get rid of this problem. So the periodicity is still there. So when you want to do loops, when you want to do renormalization, because quantum field theory on the anti-de Sitter manifold is only used at 3 levels. So all this ADS-CFT correspondence is mainly concerns 3-level quantum field theory. But when you want to do loops, this puts a serious difficulty in the game. So so this boundary, unfortunately I don't know how to use this thing. This boundary at infinity is where the asymptotic conformal field theory lives. But because this is supposed to be a correspondence between a strongly interacting theory and a 3-level theory, you don't care about renormalization maybe. But if you want to renormalize the theory, this fact of the covering will not help you. But the point is that I don't know how they do compute the beta functions. Yes, yes. Yes, it is still important. Sure. But this is an open question. I mean, there is a lot of things to do if you want to enter into the subject. So, okay. But this is an important technical question, but still on the de Sitter side there are more things which are less, which are really not intuitive. I mean, if you think in Minkowski, if you have a Minkowski mind, you will be wrong one day or the other.
Naively go out to the opinion.
The only point is that you have to know if this has anything to do what you want to do. You can do what you want, but I mean, because the because because you are still thinking in the Minkowski way, and this is not, to my understanding, the right way of doing. By the way, I can show you the difficulty. There is a calculation that you can do in the Euclidean. No, I don't think it is wrong, the calculation. I think it maybe has nothing to do with the real world anti-de Sitter. There is nothing about that.
So that's why you can't go from
Where? In the anti-de Sitter, in its covering, where? Because it did. Alfio, it's a topological problem. It's a topological problem. You can say that you don't care, you live in the Euclidean. This is your choice. This is not mine. In the Euclidean, yes. And there is not, that's probably. No, there is nothing wrong. It essentially has nothing to do with the Minkowskian. But it's not wrong in itself. So I have just 10 minutes, so I'm way too late. So, okay, but this is, I want to repeat this point still, because this is important. When you learn, quantum fields, as you know, are singular objects. They are not defined at point-like configuration. You need to smear them, okay? And if we're talking about linear theories, which are indeed the ingredient of perturbation theory, so it is important to start with this. There is one thing which is intrinsic to the theory, which is the commutator. The commutator is algebraic. So if you have the field equation gives you a unique commutator if the manifold is globally hyperbolic. If you have a manifold which is globally hyperbolic, and you have, let's say, the Klein-Gordon equation, the solution for the commutator is unique. So the commutator is uniquely fixed by the Lagrangian. Let's say this way. If you have a Lagrangian, you have a unique commutator. But then you want to quantize your theory in a Hilbert space. So you want to constrain the states of the theory. The easiest way to me to understand this problem is that you have to solve a functional equation. So you have to find a two-point function which is going to be interpreted as the two-point vacuum, let's say vacuum in tra virgolette, vacuum expectation value, the reference state expectation value of your theory, and this is the thing that you are going to use to build your green functions, to build your amplitudes, to build the norm of your states, everything. Now, because the system is infinite dimensional, this equation has infinitely many solutions. also in flat space. This is not a problem of curved space-time. Of course, in flat space, you have enough other criteria to uniquely choose W, or not uniquely. For instance, even in flat space, you have at least one possible two-point function for every temperature. So there are many, many choices, even in flat space. Of course, thermal fields are not Lorentz invariant. So if you impose Lorentz invariance, you just get the vacuum. Okay? So it depends on the criteria you impose. But even in flat space, this equation has infinitely many solutions. So the problem of quantum field theory is that the Lagrangian does not say everything to you. It says the commutator. It doesn't say which solution you have to choose among the possible ones. So as I said, this is going to be interpreted as the vacuum expectation value of the product of two fields. And in the case of free fields, this encodes all the knowledge about your theories, because the endpoint functions are built in terms of the two-point functions. So one thing that is common in quantum field theory is that the various physical properties of the two-point functions can be encoded into certain analyticity properties of the same two-point functions, which is extended into the complexification of your manifold. The complex Minkowski space, which includes the Euclidean section, or the complex de Sitter space, or the complex anti-de Sitter space, for the cases which are of interest to us. So in particular, so there are these algebraic properties of the two-point functions, but this particular property which I was mentioning too is referred to as to the spectral property. The spectral property in the standard case is a requirement of the positivity of the energy operator, which translated into a certain analyticity property of the two-point function for free fields. And this encodes all these things indeed. So let me show, I don't do this. This is an easy calculation. By the way, these slides are available on the website of the school. So you see, even when you solve the Klein-Gordon equation in flat space-time, you make a choice. You throw away the negative energies. And throwing these negative energies away allows you to extend the two-point function into a wider region of the complex Minkowski space. So the first point has an imaginary part pointing in the backward tube, and the second point has an imaginary part in the forward tube. This, you can think that this is some mathematical nonsense. This is exactly equivalent to the requirement of positivity of the energy. I'm telling here the energy is positive. I'm not telling anything else. So if you do this in flat space, then you see that because of Lorentz invariant, your two-point function is indeed the function of one variable, which is the difference variable square, and it is analytic in this plane, except from this cut. And this cut encodes locality. I mean, the fields do not commute at space-like separation. If you have no cut, you have no quantum theory. So the cut is essential. And the cut tells you that the fields do not commute at space-like separated points. Okay. Do not commute. Do not commute, sorry. Do not commute at time-like separated points, sorry. Step back. This is the space-like separated points. This is the extension to the complex manifold. This is the region where the field do not commute. Okay, the cut. Sorry. So we now, how much time do I have? 2 minutes. I will start this tomorrow.
Questions?
I have a very naive question. Can you remind me what global hyperbolic means?
Globally hyperbolic means that, you know very well, for the students, the Cauchy problem has to be well posed. There is a global, the space-time, one equivalent way to saying is that the space-time is foliated by a family of global Cauchy surfaces. This is not the case for the anti-de Sitter manifold. You see, the anti-de Sitter manifold, this equatorial section has a Cauchy development, which is a diamond. While in Minkowski space, every line has the whole Cauchy development is the whole Minkowski space, and this is the same in the de Sitter case.
There's a boundary, information can come in from the boundary.
Exactly, because of this point, because you have this is not globally hyperbolic, there is information coming in from the boundary.
Can you comment on this non-positivity of the energy and its role in the counterpart of this problem in the Sitter space?
The non-positivity of the energy, for instance, there is one thing which is underappreciated for me yet. The non-positivity of the energy opens the possibility of tachyonic fields on the de Sitter manifold, which are perfectly well defined. You solve the Klein-Gordon equation with a negative mass square. So this you can do for any negative mass square, but if this mass square is integer, then you can solve in a de Sitter invariant way. So for instance, there was mentioning by Cedric yesterday the so-called Iguchi bound. So he mentioned the Iguchi bound, telling that the kinetic term has a wrong sign, but wrong with respect to what? To the positive mass. But once you know that in the de Sitter manifold you can have negative square mass, there is nothing wrong there. You see what I mean? And this is a consequence of having having opened the negative energies. And the negative energies also reflect themselves in the existence of the de Sitter temperature.
Any further questions?
I don't hear the question. The Lagrangian gives to you, the question was, how do you get the commutator from the Lagrangian? The Lagrangian gives you the equation of motion. And then you solve the equation of motion for an anti-symmetric distribution having initial condition equal to delta in phi pi equal delta. This means canonical commutation relation. So the solution for an anti-commutator being anti-symmetric and having this initial condition is unique. This is a theorem on partial differential equation on the in flat space is known since Cauchy, and I can quote maybe Dimock for a complete proof in general curved globally hyperbolic manifold. So it's a matter of the unicity of the solution of the equation, and the equation is uniquely given to you by the Lagrangian. But the equation for the field, which is also given to you by the Lagrangian, has no unique initial condition.
Okay, so let's thank Ugo for the talk. And the next speaker is Nacio Bediaga.
Ok?
Acho que a ponte laser é que avança e volta.
Avança e volta.
Ao contrário, aí avança embaixo e volta em cima.
Tá. Avança embaixo. Okay, let's start. Thanks, Barnovelo, to invite me to present as something not standard for this school. By the way, I'm looking the Hugo presentation. I'm trying to go at least 4th dimension below, so at particle physics. Okay. Well, I start just talking a little bit about the general question about CP violation. We have a beautiful course from Professor Branco about this, but I'd like to point out something that's important for my presentation. I'd like to discuss what's this dynamic of CP violation. Professor Branco presented the Kobayashi-Markov matrix and everything, but I'm trying to focus how the CP violation come out in particle physics. So more than the Kobayashi-Markov, the phase of Kobayashi-Markov, how it appear in particle physics. Since it is a school, I'd like to spend 5 minutes to talk about particle detection. That is important to people understand how we get information from a detector. And then I'm going to the main part of this seminar, that's CP violation. You have meson three-body decay. Then I explain. And finally, I'd like to talk about the future, the LHC Run 2, that's finishing this year, and the perspective. In particular, I'd like to present an idea that I produced a little bit for this presentation. Just enter a little bit in your subject of this school. Well, the general question about CP violation, for me, is very important. The start to the CPT theorem. This is a basic theorem that I use in all seminars. CP violation, CPT theorem values for invariance theory, where the observable is represented by Michian theorem. The CP violation means T violation. That means irreversibility. That's important at the end of the seminar. It means also the same mass and lifetime for particle and antiparticle. This is a base that I use a lot here. And important also that we learn with Branco is CP violation is a phase, but it's a weak phase. Weak phase means change signal when you change the charge of particle or use the conjugation particle. So the Kobayashi-Markov we learn with the Branco, but there is some mixing between 06 quarks. We have 4 parameters, 3 angles, and 1 phase. For me, it's important. One paper in the 1981 by Big and Sanda that showed that in this new mixing matrix, the B particle have the biggest part, must produce the biggest part of the CP violation. So before the B, we have some CP violation involving strange quark, but it was 1/500, the probability of the. And CP violation in bottom should be much bigger. In fact, since then, there was building two dedicated accelerators for B particles, the standard Babar in Stanford, and in the 2000 decade, and in Japan, the cake. It's the experiment bed. In 2010, 2020, LHCb, that is the collaboration that I am involved, and now, just this year, beginning to work in Japan, the Bell 2, that's a beautiful machine with a high importance for neutral particle, that LHCb is not good. In fact, with the first measurement, when the people look at this particle channel, the B0 in K plus pi minus, they observe 8.2% of the CP violation, a big amount of the CP violation in this decay, how it was say by big sound. There is another manifestation, but I think it is very clear manifestation. Well, how about the dynamic of the CP violation? So you know that there is a weak phase, but a weak phase, as we know by quantum mechanics, we need some interference to observe this phase and to produce some manifestation of this phase. The most popular way to see CP violation is the oscillation. For example, K0, K0 bar. You have a K0 where double W exchange and go to K0 bar. Or more recently, BS bar, through this kind of the Feynman graph. If you look at the neutral particle, in antiparticle decay in the same final state, for example, pi minus or J psi, or K plus J psi pi, K plus K minus. In this case, you can use this master equation where the particle goes to a final state through a T matrix, and this is wrote in the P0 goes to alpha, plus a P0 bar goes to alpha through oscillation. The same thing for the antiparticle. Triangle. Okay. Branco talked about the beta angle, and in fact they use the B0 J psi K short, B0 J psi K short, and observe this difference in the lifetime using the tagging, and this. Okay, tá vendo aqui? Okay. And you can see this you can see this beautiful interference way, and you can look at the sin beta about with this measuring with this precising. So this way to observe this dynamic is very well known and very well established. People are thinking to use the same thing, for example, for CP violation in the neutrino sector. Well, let's go to the main thing in this seminar. It's a different way, a different dynamic to observe CP violation. If you look, for example, to B0 to K plus, you have this different final states. B0 and B0 bar goes to different final state. So you need two different amplitudes or mechanisms to produce the same final state. And it's important to say that here I need a weak phase, like the oscillation, but I need also a strong phase between these two to do this interference. In fact, the equation you have to the particle to the final state is a sum of two different amplitudes. The same thing to the final state for the antiparticle, and change signal when you pass to particle to antiparticle in both things, and we take the observable, the difference of the amplitude, square amplitude. You have to see of the difference of phase strong and weak phase. So in this direct CP violation, you need two phases: weak phase that change signal, and strong phase that don't change signal. But the observation is much easier. So here you have the direct CP violation for K plus pi minus and B0, BS K plus pi minus. It is published by LHCb in 2013. It's just count the number of events in a signal. So you have here the signal of the D0, this D0 bar. You count the number of events D0 and D0 bar, you can see that there's less events in D0 bar than D0. B0, sorry. And the same thing in a little signal, but a very significant way. And the BS, that's much bigger than BS bar. So you take this simple equation and observe 8% for the B0 in K pi, and 27% in BS in K pi. So that's a way to observe direct CP violation. How it is produced? In principle, you imagine that you have two possible ways to arrive to the final state, and this one has different weak phase and different strong phase. Let's go to particle detection, how we do this mass spectrum. When you have a collision in LHCb or in another accelerator, you have, in general, the MOX is the gluon-gluon interaction. The gluon produces a quark and quark, the list of these quarks. And there is a fragmentation of the another quarks and the gluons in the proton, and you have a lot of decays and so on. At the end, you have in a LHC energy about 100 particles at the final state. The problem is the 100 particles you can observe in a detector. It has to have a lifetime bigger than 10 to minus 10. Otherwise, it do not pass in the detector, and so decay before to be observed. And there is a few particles that are able to do this. If you look at charged particle, that's the best one to be observed. You have a proton, electron, muon, meson P, of course, charged meson P, and charged meson K. The neutral particles, the photon, neutron, and K. That's all particles that you can observe directly in the detector. Another 100 or 1,000 particles is in particle data group. We have to observe in an indirect way. This is a schedule to the detector. There is a drift chamber that observes all charged particles. There's calorimeter with able to observe photons, electrons, and hadronic calorimeter also to observe hadrons, and finally muons, observe muons. So how I can say that a particle was present in our final state? I can use a very simple mass equation that I'm talking about the Z0 minus that is a very beautiful result. It's just looking at the two muons that closing in a point, and if you take the quadri-momentum conservation, you arrive to the mass of the Z. So the Z was observed, the Higgs, everything is observed through the decay particles produced in the decay, in this decay. So we use this Lorentz invariant equation for the mass. When I get a lot of collisions, and I have it then this figure that's the mass plot of the Z0, and we fit with a Breit-Wigner this function. So my detector is important. Is important to my detector. We have to know the nature of the particle, to know that it's a muon, pion, kaon, and so on. It's important to know the angle, the three moments of these charged particles, so understand what's the origin, and knows about the neutral particles. So basically, all detector has these three important functions to do my invariant mass. And that's why I presented the results of B0 and BS in K pi, and that's the count of events. Well, let's go to the CP violation charge meson, charge heavy meson T-body decay. It's the same thing. Now we have three particles in the final state. My invariant mass is the sum of the four moments for these three particles. I have also an invariant mass like a two-body decay. But I have an important issue, important tool that I can understand better what's happening in the middle of the interaction to produce the final state. I have the invariant mass for two particles, and I have a global link of these three invariant mass, so I reduce my variables to two variables. And then I build in this plan that people call Dals plot. In the Dals plot, I can observe some intermediary states that produce my final state. For example, the K pi pi is able to produce a rho particle is an intermediary state particle, or F naught, or so on. So when I look at the Dals plot, that's the phase space plane, what is out of the plane is a resonance or another kind of intermediary states. In fact, when I look to the, for example, B in K pi pi, I have intermediary states. That's intermediary states. Here is the plane with some amplitudes. That's a picture what can occur. But the important thing is the coherent sum of amplitudes. I have many amplitudes with coherent sum. So coherent sum means interference between intermediary states with different weak and strong phase, and look at the CP violation. So when I look at the Dals plot, I'm looking for interference between many intermediary states. The representation of this this resonance is a Breit-Wigner, and is a process like this with a propagator that I represent by a Breit-Wigner, and I can produce this Dulles plot. It's the ability of Dulles plot to produce or see, observe phases, and it is the ability to observe the interference. This is only one amplitude. This is one with a little amplitude crossing that's changing with a positive interference. This one is two amplitude crossing that are big constitutive interference. And with another different way, you can have a destructive interference, and you see a hole where they both close. So it's a beautiful way, it's an easy way to observe interference and so phases. Here is a simulation for a decay. You can see I used a weak phase difference, and you can see this, the positive and negative map are different. So this difference means CP violation. To do this data, we have been working in this collaboration. LHCb at LHC is one of the four big detector in CERN. The amount of data is 10 times more Beren-Babar, and he is 800 collaborators, more than 50 institutions, and local total cost of 100 million Swiss francs. Let's go to data. Our data, the data I present here was produced from people, LHCb, in Rio de Janeiro. So it's the people call Rio's group, LHCb. First, let me start with these two more important decays, BK pi pi and BKKK. Note that the quantum number of these two decays are the same. So it's important to have a communication between them. When I look at the three chaos, the B minus and B plus, you can see the B plus, there's much more events than the B minus, and I get an inclusive CP violation about 3.6%. But if I take the events in the signal region and put in my Dulles plot, that's, I think it's the interesting things. I can do a Dulles plot with beams with the same number of events in each beam, and then I divide the positive and negative using the same beam I used before. And then I subtract these two Dulles plots. So it's a simple subtraction. The subtraction that it is not zero means CP violation. So you can see a strong region, a large region with a strong CP violation in this region. You can see also this yellow, this is a positive CP violation. Here is a negative one. I can also project, integrate in this direction, and observe the difference there's a big difference between the positive and negative. It is a CP violation. The convention is a negative CP violation. And when I go to another channel with 108,000 events, the K pi pi, do the same thing. I have 2.5 total CP violation. But when I look at the Dulles plot, I can see a red one and blue, and the green is supposed to be blue, supposed to be blue. And when I integrate, I have in the same region a CP violation, but with a different signal. This is a K pi pi. there are another two channels with the same quantum number, kk pi and 3 pions. It was published. Here is the kk pi. There's a big difference between positive and negative, which is 12% CP violation. But it's amazing. This plot appear in many places in CERN Korea and so on, with a huge amount of events in B plus and a little one in B minus, with this blue region of CP violation. The last channel we analyze, it's the B and 3 pions against some CP violation, total CP violation. But when I look, this is a much rich amount of CP violation. It's basically all things it has CP violation in this plot. Again, this region, particular region, I can see a CP violation, but I can see also that's a red one close, very close to the blue one. So a positive just very close to the negative one. When I look at the 4 channels together in this region between 1 and 1.6, I can see that the KKK, there is a negative CP violation, also in the KK pi, and a positive one in 3 pions and in K pi pi. There is some correlation that call our attention when we look. It's just in a particular region of the Dallas plot. To understand this kind of CP violation that was not in the Branco's book, that's a complete non-natural CP people expect, we begin to think about what is happening with the why this correlation we observe. The basic idea we get looking at the CPT invariance. When you look at the CPT invariance, that means the same mass and same lifetime. So when we have so the same lifetime means the total amplitude square, the sum of the total amplitude square has to be the same for particle and antiparticle. So if I have a channel with a CP violation, that means gamma 1 bigger than gamma 1 bar. To conserve CPT, I have another channels to be less than the antiparticle, in the way that the sum of particle and antiparticle to be the same. In exact proportion, CPT is exact symmetry, so I have to do this correlation between them. This what means? It means that it imply a necessary communication between CP violation channels. So when I look to the one channel with CP violation, there's some communication with another one with opposite CP violation. And the strong interaction, it can be produced by rescattering. So it's normal to have the rescattering between 2 hadrons, produce another 2 hadrons. In fact, the equation I presented in the beginning of this seminar, I have this equation is not complete. I have to put together with this equation something to explain how another channel is violated in the same amount with different signal. For this, we get a beautiful paper for Wolfstein in 1991. They used the idea of rescattering, so a particle goes to final state alpha, it's a simple idea with only two final states. The particle can go to beta final state, but rescattering to alpha, and the particle can go to alpha, rescattering to beta, and the particle go to. This is a famous S matrix of the scattering. It's the off diagonal are equal. There is diagonal term. When you write down the equation for this S matrix, you can see that there is the probability of the P goes to alpha plus the probability of the P goes to beta and then to alpha, and so on. Look, that's this equation, these two equations for both sides, seems look like the equation for the CP violation when you look at the master equation for oscillation. It's beautiful because there's a similar way to represent the amplitude. In fact, when you put together, you have the sum of the CP violation observed in P goes to alpha must be the same, plus the CP violation in beta must be 0. So he link these two decays to this the matrix S matrix. In fact, we look at the old data, the data in the beginning of the 80s, and people observe in a region between 1 and 1.6 are rescattering between pi goes to kk. Just in the region I present here, so you can see that between 1 and 1.6, basically the same shape when you subtract these two. So we discover with this paper the results that there is the CP violation are induced by rescattering for these two particles. Another observation we could do. Tem quanto aí? 16 minutos. Tem? 14 minutos. Another thing we observe is the S&P interference. This one, when I look at this particular region, you can see that the red and blue CP asymmetry, red is a positive and blue negative. When we look at this region that has an angular distribution, we can see in the integration of the region there's a huge CP violation, positive CP violation here. This is the two positive and negative. This is subtraction, a positive one, a 0, and a negative 1. And another part, the part below, that's the same thing but with opposite signal. It corresponds to the angular distribution using in the amplitude. So it is some interference between the rho that's live in this region with some amplitude with different weak phase and different strong phase. And by the way, it's a beautiful interference, quantum interference. To explain this is very easy. We could explain very easy. If you write the amplitude, the sum of two amplitudes, one, the rho particle but non-resonant, just a scalar one. If you put together, put a square, you are able to explain this this interference phenomenon. We look also in the k pi decay. And there is here we have a rho, but you have another important amplitude, the F0 980, And then you can see two zeros that correspond to interference. You can see a different present. If you look at with details in this region, you can see that the amount of CP violation, a huge amount of CP violation, is 60% of CP violation just in a little part of the Dulles plot. Putting together scattering S and P interference, we fit this all plots. I did it with some theoretician colleagues, and here you have this explanation, a beautiful explanation to this data. Now, in this moment, our group is working to do the same thing, but in 2 dimensions. So looking into the dimension. This I plot in 1 dimension, so integrate. Now we are much rich and much more difficult. We are doing this. Well, results summary before to present the last part of the presentation. CPT constraint must take in account 3-body charmless decay. Rescattering amplitude is playing important role. S&P wave hadronic interference has a clear signature in variation. In hadron-hadron interaction since the dominant dynamic in 3-body decay. That's our main conclusion we have. Future, let me talk about future. In 2010, 2012, we take 3 inverse of femtobar that give this amount of events for each signal, 108,000 for K pi pi, and so on. The run 2 that begin in 2015 and finish at the end of this year should get 5 inverse of femtobar, but this 5 inverse of femtobar with 13 TeV. That's about twice the previous run. And the cross section from B is basically 2 times. So what I expect in the run 2 is 600 and this one. So basically at the end of this year, we are have 4 times more events than putting together run 1 and run 2. So it's able to do in detail what's happening in this region and create and parameterize and create some more details, this function that we fit the previous data. We can look at the details, for example, if there's another particle crossing this region, the sigma particle. And we can look at these CP violation signatures in this region, this one, that we cannot understand. We're trying to do a la Wolfstein. Also, the DD goes to HH to explain this kind of CP asymmetry in the high part of the Dulles plot. To finish, I'd like to talk this idea that I have developed to the run 2. The idea is we have a lot of CP violation, a huge amount of CP violation. And once I present here in CBPF, even ask me, why not CPT? Look at CPT violation also. If you have so big amount of CP violation, maybe you have some CPT violation. There's no way in this decay to look at the CPT in a direct way, but I'm talking about the possible to look at the CPT based in the idea, if you have CPT violation, you have Lorentz invariance violation. So I cannot see CPT here, but I can see Lorentz invariance. If you have a Lorentz non-invariance introduced, this is a very well-known paper, the Kosteleski and so on. If your equation, P, this Lorentz goes to something proportional to P, and if you go back to our mass equation that I assume Lorentz invariance, if you have a change, something different from P2 over M2, if I just change a simulation that if you put a lambda, a constant, you can see the shape and the position of the mass plot change. But I put some dozen of MeV, so it's a big Lorentz broken. Probably it's I will not have some so big Lorentz broken, and I begin to look at old paper that people are interested just in Lorentz non-invariance. It's a idea of this block 7 in 1974. The idea is when you go to a little distance, maybe you are in front of some anisotropy of the phase, the time, the space, and the Lorentz is not anymore conserved. So these two, Lundenberg and Hede, proposing in 1968, looking at the lifetime. Lifetime is a very good measurement we can do. They propose to do this in the P on decay. Lifetime is not invariant quantity, so we need to observe. We put the lifetime in the rest mass of the particle, but we get in the laboratory, we have to do a Lorentz transformation to put to the rest mass to compare. So the idea of this guy was to move the lifetime in the laboratory, that in general is given by this gamma, to a kind of expression with a particular distance, a characteristic distance. That's the idea. There's some experiments looking at this possible non-invariant, non-Lorentz invariance in these particles. You can see that the amount of the alpha, the upper limit of this decay is changed between 10 to minus 5 to 10 to minus 17. I take data from the LHCb, a signal similar to us, and the lifetime with 200,000 events. It's 4 times less than we will have with run 2. And I can see a measurement with a very little statistical error. If I look at this decay with 800 events or 600 events, sorry, to take the events with 100 GV, we can test the possible Lorentz non-invariance at the level of 0.1%. That means I can see Lorentz invariance at the distance of 10 to 70 centimeters. Oh, that's what I'd like to present. It's welcome the run 2 data. It's a beautiful data, much beautiful than the run 1, and with a big amount. We can deeply understand the hadron interaction contribution in CP violation. I think we can do a step more. A new source of CP violation in that space, and search for of possible indirect CP, T asymmetry, and Lorentz invariance in this decay. Thanks.
Questions?
How do you measure the velocity of the decaying particle? You have enough precision on that? To test the CPT breaking, I think.
I have this moment. To do the invariant mass, I need
No, but to go to the frame, you need the velocity. To go the rest frame of the particle.
You are talking about lifetime or?
Lifetime.
Lifetime. I have.
If there is any breaking of Lorentz, it should be really small. Otherwise, we know that.
There's no precision.
So, Ignacio, is there a particular model that suggests a functional form for the lambda? It's constant or quadratic in the energy, or? Yes.
Very, very, very. But I think not plan. Possible deviation
But at much lower energy scales than Planck, of course. Any further questions? So let's thank Ignacio again. So we resume tomorrow at 9.